Hello everyone. In this video we will see about how to find the area in polar coordinates using double integration. We will recollect that when we are using the Cartesian system, that is the system of x and y, the area is given by the formula double integral dx dy. So this is the formula for area in Cartesian system. Now we want to evaluate the same using polar coordinates. So what is polar coordinates? Polar coordinates is also one more system, but instead of this x comma y, we deal with r and theta. R is called as the radial distance and theta is the angle from the baseline. So there can be an easy conversion of problems from the Cartesian to the polar and from the polar to Cartesian. But why do we need this transformation or change? Some problems which may be difficult to work in Cartesian system may become or turn easy when you convert it into polar coordinates. Hence, we will be requiring to know what is the relationship that connects the Cartesian to the polar coordinate and how to change it. Now we know that x, the Cartesian value, is connected to this r and theta by means of x is equal to r cos theta. Similarly, y is connected by r sin theta. So when we have x square plus y square, this will be r square cos square theta plus r square sin square theta. Hence, if we take r square common, it is cos square theta plus sin square theta. We know that cos square plus sin square is equal to 1. Therefore, we have x square plus y square equal to r square, or our r is going to be root over x square plus y square. Now this gives the relationship for conversion from Cartesian to the polar coordinates. And how to get back over here, so the reverse relation will also work. So we know that now r can be expressed in terms of the reverse variable x and y as x square plus y square. And now when I divide r sin theta by r cos theta, what I do over here, r sin theta is nothing but y and r cos theta is nothing but my x. R can be cancelled off. We know that sin theta by cos theta is tan theta. So tan theta is y by x. Therefore, I can write theta to be tan inverse of y by x. Hence, we have the relationship x is equal to r cos theta, y equal to r sin theta from conversion from Cartesian to polar. And for the back conversion, we can make use of the formula r is equal to root over x square plus y square and theta equal to tan inverse of y by x for the reverse transformation. Now coming to the formula for area. We know that the formula for area in Cartesian is given by dx dy. But when it turns out to polar coordinate, then it will be equivalently transformed as wherever we have dx dy, that gets replaced by Jacobian times of dr d theta. So this Jacobian is a quantity that aids the transformation, and when we find the Jacobian between x comma y and r comma theta, Jacobian is given by xr x theta yr y theta. So this will be with respect to r, x on differentiation is cos theta, with respect to y, r on differentiation is sin theta. This will be with respect to theta, you can keep your r as such, cos theta on differentiation is minus sin theta, and y with respect to theta, keeping r as a sin theta on differentiation, is cos theta. Cross multiply and you can subtract. So you will have r cos square theta minus of minus makes it as plus r sin square theta. Therefore, when we take r outside, we have cos square theta plus sin square theta. So the value is going to be equal to r when we have cos square plus sin square to be the identity 1. Hence, we now get the formula dx dy converted to Jacobian times of dr d theta, and the Jacobian value is nothing but r. Hence, when we convert from the Cartesian to the polar, the area in the polar coordinates will be given by Jacobi, which is going to be r dr d theta, first integral for our r and second integral for our theta. So the area in your polar coordinates is given by double integral dr d theta. Now we will learn about some standard curves in the polar coordinates. The first curve we will be learning is r is equal to a. What is going to be r is equal to a? It is going to be a circle with center 0, 0 and radius equal to a units. So how does this circle look like? Center 0, 0 and radius is going to be equal to a units. So that's our standard circle which we will be having. Okay, with center 0, 0 and radius equal to a units. Now how to fix the limits for this circle? So we need to move in the radial direction for finding the limits of r, and we will have to fix the limit for theta in the angle direction. Now from the center to wherever point I measure on the curve, I will always be getting, what is this name of the curve? R is equal to a. So when I have the radial line to be fixed, the radial line now moves from 0 to the upper limit a. So the limit for r is fixed as 0 to a. Limit for r is fixed as 0 to a. Now coming to theta. What is theta? Theta is the angle which is swept by this line. We need all the four quadrants, and we know that this baseline gives theta equal to 0. This above line has theta equal to, when we move from here to here, it is 90 degree. So it is pi by 2. So when we move this theta covering all the four quadrants totally, how much degrees we would have moved? We would have moved 360 degrees. So theta varies from the baseline, which is 0 to 360 degrees. So it will be given as 2 pi. So the area of the circle can be measured as r varying from 0 to a, theta varying from 0 to 2 pi, r dr d theta. Now let us move to the second curve. This curve is given as r is equal to a cos theta. How does this curve look like? So this curve is fixed entirely to the left of your axis. So let this be our baseline. Then the curve r is equal to, I have missed this a, we will add it, r is equal to a cos theta. r equal to a cos theta is going to be a circle of this kind. Okay, now coming to this circle is called as r is equal to a cos theta. Now let us measure what is going to be my r and what is going to be theta. From the center to wherever you move, this curve is referred by the name a cos theta. So my radial distance will be from 0 to a cos theta. So 0 to a cos theta. And now coming to the angle, this is going to be 0, this is going to be pi by 2, and so what can you call this lower limit as? It is minus pi by 2. When we measure the angle is always measured in the anti-clockwise. So from here to here, how much is going to be the angle? The angle will be from minus pi by 2 to pi by 2. So when you fix your limits, you can fix the limits for r as 0 to a cos theta and theta varying from minus pi by 2 to pi by 2. Now moving on to the next curve, third curve, r is equal to a sin theta. We will see how this curve looks like. Okay, so having the baseline, this is your axis and this is your axis. The curve r is equal to a sin theta is going to be a circle that is present entirely to the top of your axis. So this is the circle. R equal to a sin theta. So now when I am going to measure my r and theta for this, what will happen? I can measure this name of this circle, wherever you touch is going to be a sin theta. So from the base to the boundary, what is going to be my value of r? My r will be varying from this base 0 to the outer curve, which is the circle, which is given by a sin theta. So it is a sin theta, and theta varies from where to where theta varies? It varies from this baseline to this end over here. What is this baseline called as? Theta equal to 0. And what is this baseline, this line referred as? Theta equal to pi by 2. When you move to this point, what is theta equal to? 180 degrees, which is equal to pi. So theta will be moving from 0 to pi for the circle r is equal to a sin theta.